Going to look at practice question set number 11 last night, the longest one we've had, 10 questions. Starting with question number 1 here, which is a bit of a different diagram than we're used to seeing here. We got a positive charge and a negative charge, and we got some lines with arrows that are joining them together. Those look like they might be electric field lines. And in fact, if we read down through the question, it tells us they're electric field lines. The dotted lines don't look like anything that we've seen before. As it turns out, they tell us what those dotted lines are as well. They're lines that show areas of equal potential, equal electric potential, which remember is related to energy. Okay. Now that's not really critical for this question. In fact, it's not even necessary at all for answering this question, because this question is not about the difference between electric fields and electric potential. This question is about the difference between vectors and scalars. And we've seen questions like this before. They looked a lot different than this, but you remember on your last unit test and on your last unit assignment, both of them had a question that said the following are examples of vectors or of scalars. I can't remember what it is. This is the same question. Right? This is the same question. Do you know the difference between a vector and a scalar? That's what this question is about. Okay, what's a vector? It has both magnitude and direction. Therefore, these solid lines, because they have an arrow on the end of them, they're vectors. They have both magnitude and direction. These dotted lines don't have any arrows, so they got to be what? They got to be scalars. Okay, so first one is vector, second one is scalar. Now, you could use some different reasoning for this question, but you're not expected to. In fact, it's not what they're looking for when they give you this question. But you could use some alternate reasoning for this. We know that, we just know that electric fields are vector fields, right? We already know that before we read this question. And if they tell us that the dashed lines result from connecting those points that have the same electric potential, we know that electric potential is energy per charge, energy per coulomb. It's related to energy. And if energy is a scalar, well, then these electric potential lines have got to be scalar fields as well. I think that's a lot harder to kind of go through that reasoning than it is to go through the reasoning that says arrow vector, no arrow scalar, but it works. Yep. Numeric response number 1. This one is a pretty straightforward one. We just got to be careful of units here, right, Dallin? We got centimeters here. We got to make sure that we convert that to meters. When we use our producer equation, E is equal to KQ over R squared, 8.99 times 10 to the 9 times the charge here, which is, what do we got? 1.2 times 10 to the minus 5. Divided by 0.04 squared. The answer here ends up being 6.74 times 10 to the 7. We could say newtons per coulomb. What's the other set of units we learned a couple of days ago for electric field? Volts per meter. Either one of those would work. In this case, we go newtons per coulomb because that's what it asks for, right? But it ends up being the same thing anyways. We're going to express this A, B, C, D, 6, 7, 4, 7. If it was B times 10 to the W, which it is not, then our answer would be 6.74. And those are the only two ways that it could really be asked. Next question. We got these bumper cars here, and there's an electric potential difference in a distance between the top plate and the bottom plate of the bumper cars. We also got masses and speeds or velocities of these bumper cars. To be honest with you, when I read this question, the first thought that comes to my mind is not electricity. The first thought that comes to my mind is the collision between these two bumper cars, because we got a lot of information about that collision. What concept could be applicable in that situation? We're not going to use it here for the question that we actually have, but it's applicable, and we could easily make a question out of it. Yeah, conservation of momentum, a collision question with conservation of momentum could easily be added to this. All right, what does the question actually ask for? Ask for the electric field between the top and the bottom grids here. This is a pretty straightforward question as well. We know that E is equal to delta V over delta D. Delta V is 120, delta D is 4. We get 30.0 volts per meter, or they use newtons per coulomb, so that's what we'll use as well. Now, which way is it? Well, we always go from positive to negative, so the electric field would be pointing downward. The answer is B for this one. Three, we got a couple of different ways of tackling this one. This way. How many people tried this one as a variable value changing thing? The original, the new value? Nobody? How many people calculated the value of each field and then compared them that way, divided them? Okay, fair enough. That's the way I'll do it then. Honestly, for me, I did it variable value changing. I said the original value, I'll do it both ways. Okay, the original value is delta V over delta D. The new value of the electric field is, what are we doing here? Delta V is half of what it was, because it's 6 instead of 12. Delta D is 3 times what it was, because it's 3 instead of 1. So it becomes 1/6 of delta V over delta D. And that is just the original value. So it's 1/6. I guess we'll call it E2 and E1. We should. 1/6 of E1. So the answer would end up being D. But you could also calculate those values. E1 equals 12 over 1.01. What is that? 1200 volts per meter. E2 would be 6 divided by 0.03, which is 200 volts per meter. And then we say 1200 divided by 200 is 6. So E2 is 1/6 of E1. So either way works there. Because we have the numbers, either way works. If we didn't know what these numbers were, then we'd have to do the variable value changing way. Next question. This one's more intimidating than hard. I think once you actually go at it and don't get intimidated by it, I don't think it's actually all that bad. It just seems kind of intimidating when you look at it here. We got a positive charge here. I'm going to make it blue. And a negative charge, I'm going to make it green. We want to find a point here, 1, 2, 3, or 4, where the electric field strength is 0. So let's draw the fields at all 4 positions here and see what happens. The field caused by the blue one at point 1 is to the left because it's away from the positive. The green one is to the right because it's toward the negative. So away from positive, toward negative. Those could cancel each other out, right? Those could balance, but we don't know yet. We'll deal with that later. Here we have toward the negative green producer, away from the positive blue producer. Those could cancel. Okay, we'll deal with that in a second. We certainly can't eliminate those 2 possibilities. Away from positive, toward the negative. Those can't cancel. Right, we want to find a place where the electric field is 0, where the electric fields cancel. Okay, they can't cancel when they're in the same direction. Away from the positive, toward the negative. Those can't cancel either. So it's either got to be 1 or 4. Which one is it? 1 or 4? Don? Why is it 1? Much greater charge, you mean? Yeah. 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 Okay. Yeah. It's basically what Dylan's saying there. If you didn't hear it or quite follow it, I think at least what you were saying. The positive charge produces a certain field at point 1. So does the negative charge. If we look at just the charge, then the negative charge would produce a much bigger field. Well, we need something to reduce the field then to make it a smaller field so it's the same field as the blue one, right? Well, it's a bigger charge, which makes bigger field, but it's also a bigger distance, which makes a smaller field, which means that the field is then going to end up being the same as what it was produced by the blue one. Okay, so it's bigger charge, but it's further away. So the net result of that is it ends up being the same field as the field caused by the blue one. So we got A as our answer here. Next question. Two parallel plates are this far apart. This potential difference. What's the force? You guys remember the Venn diagram we drew for these equations? E is equal to KQ over R squared. E is equal to F over Q. And E is equal to delta V over delta D. We got our non-uniform equations here, and we got our uniform equations here. Which ones are we going to do here, the blue circle or the green circle? Uniform or non-uniform? We got parallel plates. What is it? Uniform. So we're going to use the green equations, or at least one of the green equations. We want to find force, so it stands to reason that we're going to use the middle one, but we don't know what electric field is, so maybe we're going to use the bottom one to get the electric field. E is equal to delta V over delta D. That's going to give me 250 divided by 0.015, which gives me 16,666.67. Okay, we'll say volts per meter there. And then we're going to say F is equal to Q times E, which is my experiencer equation rearranged. Alpha particle is 3.2 times 10 to the minus 19 times this. Gives me, I think it was A, wasn't it? 5.3 times 10 to the minus 15. All right, here's a good one. For a couple of activities we've done this year, we've had to go through the analysis that we have to go through for this, but I've guided you through that analysis. Last night was the first time that you've had to go through this analysis yourself. You're given a graph here that you've never seen before. You have to figure out from that graph what things mean, how to find a value for something, and what that something means here. This is a graph of potential difference versus plate separation. We really should say not V, but it should say delta V and delta D, but we're not going to lose any sleep over that. I am going to circle this times 10 to the minus 2 and 10 to the minus 3, because when I go to calculate numbers, I'm probably going to forget to put that in if I don't draw attention to it. All right. Delta V versus delta D. We've clearly never seen that graph before, so how do we deal with that? Well, let's see what the question says. The question says, what's the rate of change of potential difference with respect to the plate separation? What's the rate of change of potential difference with respect to plate separation? What are they really asking me there? What are they asking me? The slope, right? The rate of change of y versus x, that's the slope of the graph. Now, you can use the old-fashioned way of finding the slope, rise over run. Okay, be my guest, although I'm going to suggest you don't do that. Okay, I think I showed you guys a little trick in our last unit on how to use your calculator to do this. So I'm going to show you that again, okay, if you don't remember that. If you've got data points scattered like this, it makes it more work in your calculator, but it saves you more work as well. Okay, if you have a bunch of scattered data points like this and you got to draw your own line of best fit and then you've got to calculate the slope of that line of best fit, the odds of you getting the exact correct answer are actually fairly small because your line of best fit could be off by a bit, right? You've got to use your calculator there. Even if you have just this, where everything is along the line, I'm suggesting to you that you use your calculator, even though it wouldn't be all that difficult to calculate the slope by hand this way. Okay, here's how we're going to use our calculator to find the value of the slope. Everybody do this right now, okay? Everybody turn on your calculator right now. Once your calculator's on, then I want you to hit the Stat button. Stat, Edit, Edit. So first option, Edit, and then down here we scroll down to Edit. So it's actually just Stat, Enter, because by default it's on Stat, Edit, Edit. Okay, do it again. Stat, Edit, Edit. Press Enter. Now we got a data table. And that data table is the table where we're going to put my data points. Now, which data points am I going to use? If it's scattered like this, then you need to put all of those data points in. All of them. But if you got a nice perfect straight line like this, easiest thing to do is just pick your first point and your last point. That's it. My first point is 0, 0. It goes through the origin, right? My second point, the x coordinate of the second point is 10. That is 10 times 10 to the minus 3. And my y coordinate for that second point looks to be 21. That is 21 times 10 to the minus 2. So enter those points. There's your table. My 2-point table. Again, if you have data points all over the place, you have to enter all of the data points. If it's a perfect line, just pick the first point and the last point of the line. Now, to get to this point, you went stat, edit, edit. Now you're going to go stat, calc, 4. Stat, calc, 4. Now, depending on your version of the calculator, you might have to hit enter a couple of times. You may have to hit it 3 or 4 times. Eventually, you're going to get to a screen that looks like this. Y equals ax plus b. A is 21, b is 0. That means the slope of this is 21. And the y-intercept b is 0. Everybody got that? On your calculators? Remember, stat, edit, edit. Enter your data, stat, calc, option 4. Stat, calc 4. Stat, edit, edit, stat, calc 4. And then you just got to keep hitting enter until you get an answer. Hey, what are the units for this, by the way? 21 what? We went y over x, 21 volts per meter. Okay, let's look at the question here again. The rate of change of potential difference with respect to plate separation is 21. And the units, look, they asked me for the units. Volts per meter, y over x. Now, what does the slope represent? This is where we got to do our analysis, our real analysis here. We had potential difference versus distance between the plates. You guys remember from the activities that we've done that when you're trying to figure out what the slope represents of a non-familiar graph like this, you always start with an equation. Y equals mx plus b. Delta v is the y-axis, m is the slope, and x is my x-axis. There's no b, right? The y-intercept you saw in your calculator was exactly 0. Now you're going to come up with an equation from your data sheet that has delta v and d in it. E is equal to delta v over delta d. And then just rearrange it to solve for delta v, because that's what we solve for over here. Delta v disappears because it's in both equations. Delta d disappears because it's in both equations. So my slope ends up being equal to E. The slope is the electric field strength. Some of you may have figured that out without going through that analysis. That's okay. But sometimes it's not obvious. Sometimes you have to go through that analysis to figure it out. So be aware of how to do that. Lastly, question 9. The electric field strength that's just sufficient to suspend a proton in the Earth's gravitational field is what? If something is suspended, Maria, if something is suspended, then it means it's not moving, right? And if it's not moving, it's in a state of equilibrium, right? And if it's in a state of equilibrium, then forces must balance, right? So that's what this question is saying, is that forces balance. Not fields. Fields never balance. Fields will never balance. Forces balance. What two forces balance here? What two forces are equal to each other? Well, there's an electric field and a gravitational field. Probably going to be the electric force and the gravitational force, right? We're going to say QE. We could technically say KQ1, Q2 over R squared, but like we don't know anything about the other charge or the distance. We do know the charge of the proton, and we're looking for electric fields, so Just use that experiencer equation. Force of gravity is m times g. You got the mass of the proton. G is 9.81, and E is, whoops, that's wrong. Q, the charge of the proton, is 1.6 times 10 to the minus 19. I think when you do the math there, it ends up being D, 1.02 times 10 to the negative 7.